The Fields Medal is often considered the most prestigious and highest honor a mathematician can receive, sometimes called the Nobel Prize in Mathematics. In 2014, Professor Maria Mirzakhani became the first woman to receive the Fields Medal. Her math accomplishments started at a young age. As a teenager, she was a gold medalist and perfect scorer at the International Math Olympiad. Professor Mirzakhani continued to shine in the field of mathematics until she tragically died in 2017 at the age of 40, too soon to have exhausted her potential. Math Prize for Girls would like to honor her memory and amazing accomplishments. Advantage Testing's foundation, Jane Street's Math Prize for Girls, has formally named the annual keynote lecture at the awards ceremony the Maria Mirzakhani Keynote Lecture. Our 2022 Maria Mirzakhani keynote speaker is Professor Eli Grigsby, who I'm delighted to introduce today. Professor Grigsby is currently a faculty member at the Math Department of Boston's Morrissey College of Arts and Sciences. She received her bachelor's from Harvard University and her PhD from Berkeley. Prior to joining the Boston College faculty in 2009, she taught at Columbia University as an NSF postdoc fellow. In 2014, she received the A.W.M. Berman Research Prize in Geometry and Topology, and in 2016, she was awarded a Simons Fellowship in Mathematics. Professor Grigsby's primary research interests are the mathematical foundations of machine learning algorithms, particularly those involving neural networks. In addition to her role as an academic, she is also on the board of directors of Girls Angle, a very well-known Cambridge math club for girls. Please join me in welcoming Professor Grigsby, who will speak to us about geometry and neural networks.
Okay, can you guys hear me okay? Okay, good. Okay, well, my body gets used to being on stage. Let me add my voice to the congratulations. So even just by being in this room, you've proven yourself to be very talented and very creative, and I'm very excited and proud to be sharing space with you here today. So one thing that you may notice if you do go on and do mathematics for a living, and I sincerely hope that many of you make that choice, one thing you may notice is that research mathematics involves almost no sitting in rooms, competing with your peers under time pressure to solve tricky math problems. That's actually one of that's actually, to me, one of the greatest parts of mathematics. I mean, the skills that you've developed in order to be here, the most important skill that you've developed that will serve you well in the future, whether you go on in math or not, is the skill of having an attitude of curiosity, kind of a fearless curiosity in the face of not knowing the answer. So I applaud you all for that. So the main point here is that actually doing math happens in community. And this, I think, is a pretty unadvertised part of what it takes to do mathematics. It's very poorly advertised. So my mathematical goal for this talk is to tell you just a little bit about neural networks and convince you of their importance and their power by hopefully with a concrete example that is down to earth enough that we can all appreciate it. But actually, secretly, my goal for this talk is non-mathematical, and that is really to emphasize what it is that I just said, that basically mathematics happens in community, and mathematics is creative, and the best creations happen in community. And it's more important somehow to ask the right questions than necessarily to find the right answers. Okay, so I'm going to start with a story about my daughter, Ayumi, who's in the audience, and my most recent PhD student, Gage. And I'm not sure if you can tell if it's too small, but Gage, so she defended her PhD this spring, and she's holding this algebraic topology book. I guess it turns out Gage's mom is also a mathematician, which I was delighted to discover at her thesis defense. And she brought this picture of herself as a baby in a box with that same algebraic topology book. So Ayumi, I've been kind of trying to get her fired up about mathematics for a little while, and with moderate success. So of course, I took this opportunity to ask Gage, what was it that got you fired up about mathematics when you were Ayumi's age? And she turned me on to this amazing book, which I'll also just advertise here, and it's the I Hate Mathematics book. It's actually, so it was written by Marilyn Burns back in 1975, but if you just Google I Hate Mathematics, it's freely available online. And what I love about this book is that it's a book of questions with no answers. It's just so one of the questions that I'll share here, and I'll share it for two reasons. So the question is, so imagine you are bored for the day and you go outside and you're looking for something to do. Well, you happen to have some chalk with you and you look at a sidewalk slab and you start to draw straight lines on the sidewalk slab. And you might just start to wonder, if I draw straight lines on this sidewalk slab, will I always cut out the same number of regions if I draw a certain number of lines on the sidewalk slab? This is just something that you could imagine you would do if you were just kind of wandering around as a kid. And one of the questions that got Ayumi kind of fired up, and it was one of my great moments that we sat and talked about it for a little while, was exactly this question for 3 lines. And the reason I also got really excited about it was that it happened to be at least a little bit related to the kinds of things that I was thinking about at the time. So I bring this up now also because this picture will make an appearance towards the end of the talk, as long as my timing works out okay. All right, so, okay, thank you for indulging me with that personal story. Let me go on and tell you what a neural network is. Okay, so before I say that, so again, I'm going to delay a little bit. Let me just say a little bit about what a neural network can do so that we can get excited about it. I'm not going to say too much because unless you've been living under a rock for the last 5 or 10 years, you probably already have seen some of the examples out there. But I just want to flash my favorite recent one. So this is, oops, sorry, wrong way. So this was created by OpenAI. It's a model called DALL-E. And this image was generated by a text prompt. And the text prompt is right here. So this is an image that was generated by a model, by a neural network, by a deep learning model. And it's amazing, right? It's absolutely amazing that this picture, I mean, actually, everything in this picture is sort of in the style of this very famous painting, Girl with the Pearl Earring. Okay, so that's to get us amazed at what neural networks and deep learning can do. But of course, we're mathematicians. Our job is to get amazed and then to become filled with curiosity. What's going on here? How can a model possibly do something like this? So let's all become filled with curiosity. I'm not going to tell you the answer. You have to go off and explore for a long time on your own. And I'm definitely not going to be able to really say anything much about this. But the first thing I can say is that if you're going to create something like this, well, the first thing, I mean, if you notice somehow there are some elements, and maybe you're deciding what elements to include and what elements not to include. So somehow what these learning models are doing is really taking a bunch of pieces and figuring out and making decisions about, making yes-no decisions about what to include and what not to include. Okay, so To get us started, so again, the question that I'm trying to answer here in some kind of concrete way is, what is a neural network? So in order to say what a neural network is, I have to talk a little bit about decisions. Okay, so neural networks make decisions. Let me tell you a little bit about a very simple decision model that is kind of the warm-up to understanding what a neural network is. So this is what's called a perceptron, and a perceptron is a model for answering a particular kind of yes-no question. So suppose you want to make a yes-no decision based on some weightings of some answers to a few yes-no questions. Okay, so I want us to pause for a moment and just note that actually this is kind of how we make decisions, right, most of the time. So just as an example, and this example, by the way, I'm stealing this example from this online book, Michael Nielsen's Neural Networks and Deep Learning, just because I think it's a fun example. There's a cheese festival in town, and I love cheese. Should I go? Well, you might try to break down this decision, this yes-no decision, into some weighting of the answers to these three questions. Will the weather be good? Will my friend Bob be able to go to? Is it close to public transit? Okay. What we should notice here is that actually secretly what this decision is a binary function. So we have three binary inputs in this case. 1 equals yes or true, 0 equals no or false. And in this case, there are 2 to the 3 possible inputs that there could be. And what we'd like to do is decide 0 or 1, no or yes. Should I go to this cheese festival based on this binary input? Okay, so a perceptron is just a simple model for making this kind of decision. And here's a picture of a perceptron that I drew on my chalkboard at some point. So here you have the inputs, these x1 through xn. These are the binary digits, the answers to those questions. And then you have some weights. So this is how you weight those inputs. And then there's some real number, which is going to end up being a threshold. So for some fixed weights, W1 through Wn, and a threshold B, the way that the perceptron makes the decision is, well, if this weighted sum of these binary digits is greater than B, then you output 1. And if it's less than B, then you output 0. Very simple. Okay. And also, it just kind of makes sense as a decision-making process. Now, what I want to point out here is that actually secretly there's some geometry behind this. So if you know what a dot product is, this is really just what you're doing is taking the dot product of these binary digits with these weights. And so there's actually kind of a nice geometric model for what's going on here when this perceptron is making its decision. So this perceptron is really just nothing more than what's called a linear classifier. So here you've chosen some weight vector. This is the two-dimensional input example, but you've chosen some weight vector, this W, and this threshold B. And the thing about dot products is that the level sets of dot products with a particular fixed vector is just a hyperplane. So a level set is just a linear space, an affine linear space of one dimension lower that is orthogonal to this vector W. So what you're really doing here is you're separating your space along a hyperplane, an affine hyperplane. And you're saying, okay, so here in my talk, whenever I write something in red, that's output 1. Whenever I write something in blue, that's output 0. Okay, so you're separating your space into two half spaces along an affine hyperplane. Okay, so this is a linear classifier, and this is just what I said. You output 1 or 0 according to whether you're on one or the other side of an affine hyperplane. So this is what a perceptron is doing. Okay, so perceptrons, I mean, when I say it like that, it may seem that perceptrons are pretty boring. They can't do that much. You just kind of separate your space into two very simple pieces. But it turns out, actually, that if you put them together, they are quite powerful. In fact, what I'm going to try to convince you of in the next few minutes is that they are at least as expressive as any Boolean function. So this should make you get really excited because Boolean functions are really the basis of computing. I mean, essentially, you can make any computer program with a perceptron network. So let me convince you of this fact. So elementary Boolean functions, it turns out, are all in a very natural way realizable as perceptrons. So what do I mean by an elementary Boolean function? Well, these are these very simple Boolean functions that take two inputs and have one output. So an example of this is AND. So maybe you've seen truth tables before. If you haven't, I'll just kind of break this down here. But the idea is that AND is something that takes two binary inputs and it spits out one binary output, a 0 or 1. And the way that this works is that if you think about A as being like a statement and B as being a statement, the statement A and B is true if and only if the statement A is true and the statement B is true. So the statement, I am happy and I know it, is only true if I am happy and I know it. Okay. Right, so that's an example of an elementary Boolean function. And it turns out, if we think about the two-variable Boolean inputs as the vertices of the unit square in R2, well, and it can be modeled by a perceptron. And all that I'm saying there is that the points that are labeled with 1, that output 1, in this case for AND, it's just this point, 1, 1, are separated from the points that output 0 by an affine hyperplane. And here are the equations for the affine hyperplane. Or here are some equations for an affine hyperplane that does the trick. Okay, so same thing with OR. So OR is another elementary function, elementary Boolean function. And again, you can separate the points that output 1 from the points that output 0 with an affine hyperplane. Okay, I'll just do a few more just for the sake of it. So there's if-then. This one's kind of fun. So if-then is a Boolean operation on two variables that is true unless A is true and B is false. Okay, so if A is all cows are purple and B is anything, if all cows are purple, then anything is actually a true statement. Okay. But again, if-then is also modeled by a perceptron. Okay, so, and then there's one more, which is not. This one is very important as well. So not is just true when the statement that it's negating is false, and false when the statement it's negating is true. And this is a Boolean function with a single input. So the hyperplane in this case is just something that separates these 2 points from each other. Okay. All right, so what's cool here is that you can actually construct, well, this is probably obvious. You can construct other Boolean functions by concatenating elementary ones. So, for example, you can do if A and B, then C. And it's most fun when you let A be you are happy, B is you know it, and C is you clap your hands. Okay, all right. That joke credit for that goes to Josh Green, one of my colleagues at BC. But if you want to, you can think about when exactly this statement outputs a true and when it outputs a false. Just if you're curious. Okay, so the point is, though, that all of these concatenations of elementary Boolean functions can be modeled by perceptrons. And so any kind of logical operations that you're doing, as long as you can model these elementary ones by perceptrons, you can model any concatenation by perceptrons. So in this case, you would create this perceptron network with these weights and these thresholds. And if you fed in a binary tuple, its output would be exactly the binary output that if A and B, then C outputs. Okay, so in fact, it turns out, and this is less obvious, that any Boolean function can be realized by concatenating elementary Boolean functions. So what that's telling us is that any Boolean function can be realized by concatenating perceptrons. And that, I think, is surprising, or at least it was to me the first time I learned about it. So a fun example to illustrate this, and I'm not going to prove that statement in general, but all the elements that you would need to prove that statement are in what I'm about to tell you. So again, fun homework assignment is to prove this in general. Oops, what happened? Everything okay? Okay, great. So this fun example is the XOR function. So you can think of the XOR function as being, it's kind of like when you have two light switches on in a room, and they have to both be going up the same way in order for the light to be on. If they're different, then I guess if they're in this case, if they're different, then the light is on, and if they're the same, then the light is off. You can also think about this as doing the sum mod 2 of the binary digits. So the 0, 1, and 1, 0 output 1, and 1, 1, and 0, 0 output 0. Okay, so I claim that you can model this XOR function by a perceptron network. And okay? Is it all good? Yeah, it's all good. Okay. So let's just do it. And the sort of main thing that we'll use to kind of construct what this perceptron network looks like is what I'm going to call the disjunctive normal form for this Boolean function. So don't be scared off by the words. The idea is that you make a list of all the points that get mapped to 1 under this Boolean function. So in this case, we see it's 0, 1, and 1, 0. We make a list of all of those, and then we write those as a string of inputs and not inputs, depending on whether there's a 0 or a 1. So in the case of 0, 1, what we'd see is if we want a Boolean function that just assigns 1 to a single one of these points, we just list, well, A and not B. So the only thing that will output a 1 for this function here is 0, 1. And then we concatenate that with OR with the other point that gets mapped to 1, which is not A and B. So I guess this corresponds to this point, and this corresponds to this point. And now what we've done is we've listed all the points that get mapped to 1, and then we've constructed a function that only outputs 1 when it's one of these points. Okay, so that's the XOR function, written in disjunctive normal form. And what that allows us to do is create this very simple perceptron network, where the first node here, so I'll start using neural network terminology now. Here's the input layer. We have these 2 inputs, and then here's a hidden layer, and the hidden outputs are A and not B, and not A and B. And then this last layer, what that does is performs the OR operation. So really what we've just done is just created a very simple logical circuit, and we've implemented it using perceptrons. Okay. All right, and what's also kind of fun to do is just understand what's happening in this hidden layer to these important points. Well, these points are just staying fixed, and then this point gets mapped down here. And now we're able to separate them with a hyperplane. And that hyperplane is the OR hyperplane. Okay. So I'm nearing the end of my time here, and I still haven't told you what a neural network is. But you maybe kind of started to guess that actually a perceptron network is actually just a very simple example of a neural network. The simplest. So you should think of a perceptron as being a discrete version of a modern neuron. So in other words, a modern neuron is kind of an analog version of a perceptron. So the idea here is that everything is based on these affine linear functions, these degree 1 polynomials in your inputs. And then for the various outputs, what you do is you just apply some kind of function. And this function is called an activation function. So in the case of perceptrons, the activation function, so this is like the rule that specifies whether or not a neuron fires or doesn't fire. In this case, the activation function for a perceptron that we're using is the step function. But it's really not great using discontinuous functions like this if you want to learn things. So a modern neuron doesn't use, a modern neural network doesn't use step functions. Instead, they use functions like this. So this was probably one of the first activation functions that was used. This is called the sigmoid function. And that negative z should be up in the exponent there. That's a mistake. But what's more commonly used actually is this ReLU function, this piecewise linear function. And by the way, this ReLU as an activation function has really only been around for less than 10 years. It's actually kind of amazing that it's now become sort of the main one that's used in practice. And the geometry of neural networks with this activation function is actually, as a mathematical object, the class of ReLU neural network functions is still really in its understanding of the class of ReLU neural network functions is really still in its infancy, I think. Okay, so now you know what a neural network is. It's really just what we just said, except you use something less discontinuous. And so that's where I come back to this question that got Ayumi fired up from the I Hate Mathematics book. So if we really want to understand the geometry of these functions that are sort of analog versions of these perceptrons, well, really, the answer lies in understanding hyperplane arrangements. So here, what I'm picturing is a single layer of a neural network. And what it defines for us is a set of 3 affine hyperplanes in R2. And here they are. So these are the separators between the yes-no regions of the corresponding perceptron network. And what I've written here in purple, so I've drawn arrows in the direction, in sort of the positive direction for each of these hyperplanes. And I've coded the regions with binary tuples, depending on the output of the corresponding perceptron network. And it actually turns out that this very simple picture actually gives us a lot of information about the geometry of what the corresponding more modern neural network would output. So since I'm nearing the end of my time, I'm not going to say much more. I'm just going to flash some pictures. But here's an example of this particular neural network. So again, I've coded the regions with the outputs of the corresponding perceptron network. And that is telling us what the image will look like geometrically. So the idea here is that these binary tuples are going to be telling us what face of this non-negative orthant you're going to map into for this modern neural network layer map. Okay, so I will go ahead and stop there. Here are some references, and I encourage you to go off and explore for yourself.